Today I would like to talk about a few things on probability and its application on the naive-based classification model. So let's take a look at the joint probability. The joint probability of A and B can be denoted by P, A, B, P, A, and B, or the probability of the intersection. This is the probability that both A and B will occur. If A and B are independent, meaning the occurrence of A has nothing to do with the occurrence of B, then the joint probability can be computed by PA times PB. A simple example here is a probability that if you toss a coin twice, how likely can you get the heads in a row? If we use A to denote that when you toss the first time, it turns up a head, and B be the event in which you turns up another head in the second time. So we know these two events are independent. So the likelihood of getting A and B both together is the multiplication of PA times PB. In this case, you're going to get a quarter of the chance. The joint probability here is not limited to only two events. You can actually apply the same idea to 3 or more independent events. And you can have the joint probability of E1, E2, E3, and EM by multiplying all the individual probabilities of E events. Now, this computation is only possible only if the events are independent. So bear this in mind, and it will be handy when we discuss the naive-based model, when we take the independence assumption. Now let's take a step further and look at joint probability of dependent events. And this is also relevant to the naive-based modeling. So if A and B are dependent, for example, if the occurrence of A is dependent on the occurrence of B, then the joint probability can be computed by PB times PA given B. If A and B are dependent, for example, if the occurrence of A is dependent on the occurrence of B, then the joint probability can be computed by PB times PA given B. Here the notation of PA given B is a conditional probability of A given B, or how likely A will occur if we know B has already occurred. Likewise, the joint probability can also be computed by PA times PB given A. This may look very abstract. So let's take a look at an example to make sense of it. Suppose you are running a restaurant and you look at your transaction data and try to learn something about the statistics so that you can improve your business. Now let's say you find out 90% of the customers order a burger. 72% order a burger and fries. Now you want to know if a customer already orders a burger, how likely he will also order fries? And this question is certainly relevant to your business. So to answer this question, let's use first proper notation. That A be the event that a customer orders fries, and B be the event that a customer orders a burger. So A for fries, B for burger. In this case, you know the likelihood of customers ordering a burger, which is PB, 90% or 0.9. Now you also know the joint probability that these two things will be ordered together. PA and B is 72%. The chance the customers order both burger and fries. Now the question is about the probability of ordering fries given the customer has already ordered a burger. So this is actually the conditional probability. You want to know how likely A, which is fry, will occur if B has already occurred, if burger has already been ordered. Okay, so this is essentially a conditional probability of PA given B. Now from the formula that we have here, PB times PA given B, as you can see, this equals to the joint probability of PAB. Okay, so we can write this out. And if we take both sides and divide them by PB, okay, so if we divide both sides by PB, we get PA given B equal to PA and B divided by PB. Now we know PA and B, which is the joint probability, 0.72. And we also know PB, which is 92%. So we basically divide 0.72 by 0.9, and we get the chance that if someone has already ordered a burger, how likely would this customer also order fries? So this is an application of that joint probability and conditional probability formula. Now, one step further from here, let's take the formula in blue again. So we have PB times PA given B equal to the joint probability. But we can rewrite the formula in a different way using PA times PB given A. This is also the joint probability. So these two will be the same. Now if we divide this formula, the both sides, by PB, then we get this formula in red, which is PA given B equal to PA times PB given A divided by PB. Okay, so what this formula says is that if we know the joint probability of one way, then we should be able to compute the other conditional probability. Okay, so this is essentially the Bayes theorem. Okay, so this is the formal equation for Bayes theorem. So what it says is that in order to compute the conditional probability of A given B, if you know PB given A and the probability of A and probability of B, then you should be able to compute the probability of PA given B. But why is this important? Going back to our restaurant example, it can certainly help us answer questions related to food services and business. And if you substitute the notion of fries versus burger with the notion of disease versus symptoms, it opens up opportunities to study problems such as how likely a person can be diagnosed of a disease, perhaps cancer, given the observation of certain symptoms. So Bayes' theorem is really the foundation to many applications in statistics and data analytics. And we'll take a look further into the naive Bayes classification model. So with this preparation, let's now take a look at the naive Bayes classification model. Two keywords in the name. Naive. Naive because the model has naive assumptions. The second keyword is Bayes because it takes advantage of the Bayes theorem. So what are the naive assumptions? In the naive Bayes classification model, there are two basic assumptions. One is that attributes are equally important. Second, attributes are statistically independent. The second example is especially troublesome and naive because what it means is that the observation of values in one attribute has nothing to do with those in any other attributes. They are totally independent. In reality, we know this independence assumption is rarely true. For example, in this weather data, we can see clearly that humidity and temperature are dependent. High humidity is often associated with high temperature, so the independence assumption is clearly violated here. The main purpose of having the naive assumption or the independence assumption is so that we can have mathematical simplicity when we compute joint probabilities. And practically, as it turns out, such naive assumptions do not cause too much trouble, and related models actually perform very well. So let's review the Bayes theorem using the data example here. The data is about observations of weather condition and whether a game can be played or not under that weather condition. Suppose we have had past experience about the conditions and the outcome of the game. And whatever model we build can learn from the past experience or from the data. And this is what we refer to as training data. Now let's suppose we are presented with a new data instance. Perhaps this is about today's weather condition. It is sunny, cool, high humidity, and windy. And our job or the classification task is to predict, based on the evidence of the weather condition, whether the game will be played or will not be played. Remember, we have the Bayes theorem, which says we can compute PA given B by PB given A times PA divided by PB. Let's change the notation a bit here by using H and E instead of A and B. Still the same equation of the Bayes theorem, but here about H and E. We use H and E because we want this notation to be suitable for the problem here, so that they are more meaningful instead of A and B. By H, we mean hypothesis. The hypothesis about whether the game will be played or not. So we certainly have two sides of the hypothesis, whether it's yes or no for the play attribute. E is for the evidence. What are the evidence? Evidence is the testing data that we have observed. So the weather condition here, such as sunny, cool, high in humidity, and windy. These are our evidence in order for us to make the prediction. So essentially the task of classification in the probabilistic thinking is to estimate the probability of hypothesis yes versus no given the evidence. For each hypothesis, using the Bayes theorem, we can compute P yes given E, and this is what we try to estimate. We want to estimate, given the evidence that we have, given that today is sunny, cool, high in humidity, and windy, how likely that the game will be played? How likely we'll say yes to the play attribute? Okay, and from the Bayes theorem, we can easily come up with the equation that this probability can be computed by PE given yes times P yes divided by PE. And we can do the same thing for the probability of no. Okay, so we can also estimate the probability of no given the evidence, given the observation of the data. Okay, so ultimately, if P yes given evidence is greater than P no given evidence, then we can predict yes, and vice versa. So what matters here is which value is relatively greater. Now, as you notice, PE is a common denominator in both equations, and it impacts both values proportionally. But it will not change the relation between the two probabilities, and therefore PE can be ignored from the equation. Okay? Because PE changes both values in the same proportion, but if P yes is greater than P no, PE is not going to change that relation. So we can basically ignore PE as a common denominator because we really care which value is bigger, yes or no. So with this we get P yes given E equal to PE given yes times P yes. And P no given E equal to PE given no times P no. And here the evidence, or E, is a combination of the weather condition that we have observed. Basically, sunny, cool, high humidity, and windy. So the probability of E, or evidence, is really the joint probability of these conditions together, when how likely can sunny, cool temperature, high humidity, and windy happen together. So given the independence assumption, it's easy to do that. If these attributes are totally independent, then we can multiply their individual probabilities to get the probability of the evidence. So the P yes part, on the P yes part, we get PE given yes, which can be computed by P sunny given yes times P cool given yes times P high humidity given yes, P windy given yes. Okay, so these four temperature conditions altogether become the evidence. And so the overall evidence probability can be computed by the multiplication of these individual probabilities if we take the independence assumption. And then finally, of course, times P yes, which is already in the formula. So this is our final model. And we can do the same for P no given E. Okay, exactly the same idea. Now the question is where these probabilities come from. Essentially, if we build a model, we want the model to learn from the data, especially to learn from the training data, learn from the past experience. So these probability values or statistics should come from the training data. So let's look at PS. The probability of getting yes, or how likely the game will be played regardless of weather condition, the PS in blue. A simple approach is just to count the number of yes divided by the total number of observations, and we can get the idea of how likely yes will happen. So on this weather data set, we can look at the yes answers. Okay, so these are the yes, and we also have this record having the yes outcome, as well as a few others down here. Okay. So in total, I think we have 9 data instances where we have play as yes. The outcome is yes. And totally, we have 14 instances. So the probability of yes, or P yes, the one in blue here, is 9 over 14. Now, what about the individual probabilities of the evidence? For example, P sunny given yes. How likely can we have a sunny outlook given the game is being played? So among the 9 instances where the game is played, there are only 2 instances with sunny outlook. So P sunny given yes is 2 over 9. So likewise, you can compute the probabilities for P cool given yes, P high humidity given yes, P windy given yes. And with all these probabilities, you should be able to compute the overall probability of P yes given the evidence. Okay, so we can compute the yes part. Likewise, we can compute P no given E with the same idea. Okay, and so ultimately we can compare P yes given E versus P no given E, and whichever has a greater probability should be the predicted outcome. So this is the basic idea of the naive Bayes model. And again, there are two keywords in this model: the naive, the independence assumption, so that we can model the joint probability of the evidence by the individual probabilities. This is one. The second keyword is the Bayes, okay? Because it takes advantage of the Bayes theorem so that we can model P yes given E using PE given yes among other probabilities. And this makes our modeling easier and straightforward with the data that we have here.